Well, so far in this unit, we've learned how to take exact data and write systems of linear equations using that exact data. We are also able to convert that system of linear equations into a matrix equation. And we've learned how to use the ideas of inverses and identities to solve those matrix equations. That has all been using exact data. Now what we're going to do is get into some situations where we've got dirty data. Before beginning this tutorial, you should have watched the video segment, the National Geographic video segment on Old Faithful. It's just under 3 minutes long. Today we want to talk about regression, which we'll subtitle Finding a Function Where There Isn't One. And what we want to be able to do is to take some of this dirty data and predict how long it will be before the next eruption of Old Faithful. Okay, in order to do that, we're going to measure how long an eruption lasts, and then measure how long it is before the next eruption comes. Our assumption being that the time it takes for the next eruption to occur is a function of how long the previous eruption lasted. So let's take a look at some dirty data. Here we've got a sample from a larger set of data that was actually gathered at Old Faithful. And unlike the clean data that we've been using that exactly fits some function, this data, we'll call it dirty data. And what's dirty data? Well, it's data from a real-life situation that seems to fit some function quite closely, but does not exactly fit it. As we look at this data here, well, here's our data, but as we look at the graph of the data, what would you say would be the function family that would best fit this set of data as you look at it? I think we would probably all agree that some kind of a line going up through here would be very, very close to all of the data points. Certainly closer than some, excuse me, some parabola, some cubic, logistic, or other function family. It should be pointed out here that our data, if you look over here in the table, our data is not even a function, as is frequently the case with dirty data. You'll notice that right here, 4.4 has an output of 86, and down here, when it was measured on another eruption, 4.4 has a different output of 73. As you'll recall from Unit 1, that means this set of data does not even qualify for the definition of a function. And yet, we're going to be able to, through this regression, this powerful regression progress, we're going to transform non-functional data into a functional model which will be very powerful and we'll be able to use. So let's go ahead and if we can agree on the fact that this best fits a line, then we go to that equation y equals ax or mx plus b, and we will substitute all 20 points, all those 20 x and y values from that table, into this equation and end up with 20 equations in two unknowns. Now, some of you might be saying, why would we find an equation for each data point? After all, we really only need 2 points to come up with a line. Well, if we only did it for 2 points on the line, then what we would end up with is having a line that is closest to those 2 points, but may or may not be very close to the other 18 points. So we're going to, in order to do this regression properly, we must use all of the dirty data points. And so we'll use all 20 of these data points and create 20 equations. So you'll notice that we had 4 as our input and it outputted 71 back in our data. So here's the first 5 of those 20, and that continues, so we have actually 20 equations in our system, and we've got 2 unknowns. So this is a little bit different than what we've seen in the past. All right, so what do we do next? Well, I think you know what we do next. We've got our system of linear equations, and we convert those into a matrix equation. Okay, so we end up with, since our b's had no coefficient written on them, we take those all to be 1. And we've got our matrix equation here. It is a 20 by 2 for our coefficient matrix. Our constant or answer matrix here is a 20 by 1. Okay. We call a system with more equations than variables, a linear system that has more equations in it than it has variables, an overdetermined system. And that's what we've got here. We've got far too many equations and only 2 variables, and so it doesn't even have a solution. We knew that already, since the points on the graph do not form a perfect line. You can't get a straight line to go through all of those points. So what kind of matrix do we want for our coefficient matrix if we're going to be able to solve this system of equations? Well, you get kind of a hint of this. Well, another reason why this overdetermined system cannot be solved is that the coefficient matrix is not square. Therefore, it is not invertible. Therefore, we can't find an inverse for it, and we cannot solve the equation. So, what we're after is a square matrix. Well, do we want a 20 by 20 coefficient matrix, or do we want a 2 by 2 matrix? And why? Well, if you stop to think about it, how many variables do we have? That's right. We've got 2, m and b. So it would make sense that we should try to get ourselves a coefficient matrix that is 2 by 2, a square 2 by 2 matrix. Well, could we multiply both sides of the equation that we've got here, the matrix equation we've got, by a certain matrix and get what we want? Let's see, we've got a 20 by 2 for our coefficient matrix, and we'd like it to be a 2 by 2. So can we figure out what size of matrix we should multiply by? We've got a 20 by 2. We're going to multiply it by some other matrix and end up with a 2 by 2. What should that matrix be? I think you've got it figured out. Yes, what we need is a 2 by 20 to multiply both sides of the equation by. That way our 20 in the center, 20 and this 20 match, meaning we can multiply, and our result will be the 2 by the 2. Do you remember how we do it? Showing that we'll end up with a square matrix of 2 by 2. Now the big question is can we find a 2 by 20 matrix that has some relationship to the problem that we could multiply by on both sides to maintain that equality in this matrix equation? Well, it turns out that we do have that. When we make the rows of a matrix the columns of a new matrix, we call it the transpose. So what we do is we take the rows of the matrix and turn it into columns. Or you could say take the columns and turn them into rows. Either way, you'll notice here we've got a row of 4, 1. The first row becomes the first column. The second row, 2.2 and 1, becomes the second column. Or some of you might say, oh, you take the first column and it becomes the first row. Either way you want to think about it, we end up with a matrix known as the transpose. So what we're going to do is we're going to square this coefficient matrix up by multiplying both sides by the transpose of the coefficient matrix. So, of course, being 20 by 2 and 2 by 20, we'll use our spreadsheet to do that. In doing so, we end up with a spreadsheet result here with our 2 by 2 and multiplied by our variable matrix to get our answer matrix. And what do we do next? You're familiar with this. We're on familiar ground. What do we do from here? We find the inverse, it's now invertible, of this coefficient matrix, and we multiply both sides by its inverse.